as x goes to infinity and as x goes to negative infinity. So let's look at this first one. As x gets huge, like really, really, really big, as x gets really, really big, is the 1 consequential as x gets huge? No. Is the 4 consequential? Is 2x consequential? A little bit, right? But what's the thing that's really dominant? What's the thing that's most important here? The x squared is most dominant here, right? So the point of this one is, first of all, if x gets really big, this is going to be positive, and this is going to be positive. So you know that the whole thing is going to be positive. Whatever the end behavior is, it's going to be positive. This thing right here, this square, what does it effectively do to everything else because there are no other squares? It makes everything else effectively irrelevant. Is this 0? It's not 0. It exists. Like the denominator exists. But what happens to the numerator? It gets huge, massive. It can get much, 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 much bigger. So what's a very, very, very big number over a smaller number? A pretty big number, right? So what happens to this as x gets really, really big? It gets arbitrarily big. It blows up, it goes huge, it gets really, really big. It gets really, really big. You can make this as big as you want by plugging in bigger and bigger numbers. You can tell that because the degree of the top is greater than the degree of the bottom. What's the degree of the top? 2. What's the degree of the bottom? 1. If the degree of the top is greater than the degree of the bottom, it's always going to be positive or negative infinity for the end behavior. Does that make sense, everybody? So on this one, as it goes to negative infinity, it tells you, why does it go to negative infinity in this case?
Because it has to be positive, negative, or negative, positive.
Yeah, up top, again, what's the only term that's really going to matter? This 3x squared, right? That's positive, right? But what does the bottom become if you plug in a negative number? If you plug in a negative number, what happens to the bottom? It becomes negative. So what's the only thing that changes from here to here? All positive, positive, and positive. What's the thing that changes down here? Positive and negative. So therefore it goes to negative infinity. So this is a great case to look at. The degree on top is greater than the degree on the bottom. So on the intercepts, the x-intercept is when y is 0, and the y-intercept is when x is 0. We did this yesterday. X-intercepts happen when y is 0, and y-intercepts happen when x is 0. So what do you literally do for each of these cases? You literally plug in 0 for x for the y-intercept, and you plug in 0 for y for the x-intercept. So when you plug in 0 for x, what do you end up with? Negative 4 over 3. So when you plug in 0 for x, what's the y-intercept become? Oh, it's negative what? I like writing it as a point, everybody. Write the intercept as a point, Similarly, when you plug in 0 over here for y, you get 0 equals a fraction. What's the only way to make a fraction equal 0? Well, not remove it. A fraction equals 0. The only way for a fraction equals 0 is if the numerator is 0. So what's the only way to make the numerator 0? Make x4. Does that make sense for the intercepts? Stephen? Yeah. Okay. So vertical asymptotes. Vertical asymptotes happen when at numbers where the denominator would be 0. Vertical asymptote, this yesterday happened where the denominator could be 0. So what's the denominator here? What is the denominator? X plus 3. What number makes the denominator 0? So the vertical asymptote happens when x is equal to negative 3. The trickier one is what you asked about, which is horizontal asymptotes. You have to look at end behavior for horizontal asymptotes. What happens as x gets huge? What does this whole thing get infinitely close to? 1. A billion minus 4 over a billion plus 3, they're about the same number, right? Something huge minus 4 over huge plus 3. What is that really close to? 1. So as it goes to positive infinity, it's 1. You also have to check the negative infinity. Well, what's negative a trillion bajillion minus 4 over negative a trillion bazillion plus 3? What is that infinitely close to? No. Oh, 1. Pot 1. Close to 1. What's negative 10 over negative 10? What's negative 100 over negative 100? What's negative a billion over negative a billion? They're both negative. So here's the thing. You have to check both. If both of these are 1, what is the horizontal asymptote? What's the horizontal asymptote?
1.
1 is a number. What's the equation for the line?
Limit of f(x).
Yeah, so what we could say is the end behavior. So the horizontal asymptote is y equals 1. All horizontal lines have an equation y equals 1, or 2, or 3. Y equals a constant. As this function goes infinitely to the left and right, what does it get infinitely close to? Y equals 1. Do these two functions look the same visually? Does this function look like this function? No, they don't. They don't look visually the same when you write them down. But if you take out your calculator, don't do it right now, if you were to take out your calculator and graph these functions, how many of you are comfortable graphing a function like that on your calculator? Raise your hand if you think you could graph those on your calculator. Everybody could raise their hand. You might need a reminder? Yeah. Okay, so let's graph one of them and see what it looks like. Or if it's not behaving. It's not behaving at the moment, we'll do that. No, there isn't an asymptote. So when you look at the function originally, you might think to yourself, oh, well, you can't plug in 3 into the denominator, so therefore, it must have an asymptote there. Here's the thing. What was my big hint that I gave you? What did I say to do? Factor, factor, factor. Who love to factor. The x plus 3 gets canceled out. Oh, you figured it out. Excellent. I'm not sure why it's not letting me put it up there. It's just being really annoying right now. I'll put it off to the side here. So when I graphed it on my calculator, I ended up with this. Looks like that. So what do you do to the original function? You should factor it and see what happens. If you factor the top, what does the top become? Can someone tell me?
X plus 5, X plus 3.
Yeah, and the bottom is?
X plus 3.
Yeah, and what cancels?
X plus 3.
So here's the thing. When you cancel that, it does become x plus 5. If I asked you to graph this, what do you have to add in? What do you have to add in? Well, you still can't plug in -3, right? So you go over to -3, plug -3 in here, what do you get? What's -3 plus 5? 2. So where do I put the dot for the whole? -3 comma 2. -3 comma 2. So what is actually right there? There's a little hole. So if there's a little dot here, there is a hole right there for that function. Is it an asymptote? No, because you can cancel it out. You can cancel out the term.
Why do they call it a hole?
Because it literally is a hole. If I were on my graph right now, Nick, if I were to zoom in on this, it doesn't show you a hole on this, but it's just because the resolution is really poor. If I were to keep on zooming in, you know what you would see right there? A hole. You can plug in any number you want except for what? -3, right? In this case, because the same weird the x plus 3 is on both the top and the bottom and multiplied, we can cancel it out. So instead of being an asymptote where it spikes, what happens instead? It turns into a hole instead. If you can cancel the term, it becomes a hole instead. If you can cancel the term, it becomes a hole instead. Tell me what the denominator factors into.
2x.
Oh, okay, so we know it's going to be 2x and x, right?
Yeah.
You just have to be careful now. 2x minus or plus?
-3. No, 2x plus 1.
Plus 1 and?
Minus.
Like this?
Yeah.
What should you always do, even if you're pretty sure?
Check.
Please check. Everything you do on this one is going to be reliant on this being correct. If it's not correct, you'll be really sad later. Let's check it. 2x squared minus 6x plus x minus... Oh, does it work? It does. So you are happy. So it says, state the domain. What's the definition of domain? What's the definition of a domain of a function? It's the what? It's the set of all input values. So the domain is set of all input values. You can write this many different ways. How many of you, all of you should be raising your hands, have had to find the domain of a function before? All of you. You've seen it written different ways, probably, like set notation or like line segments. I accept any, you could write it as a sentence. Usually you have to find the things x can't be. I'll show you my preferred domain. X such that x can't be equal to what? There are two things x can't be.
3.
3 or? Yes. Oh, I can almost write a half, almost. You see this bar right here? This means such that. Mathematicians love variable. They love shorthand, right? Variable. This means such that. X such that x doesn't equal 3 or negative a half. What can x equal besides everything else except for those two values? Why can't it equal those two values? Because what would be 0? We haven't done wholes or asymptotes yet, but are you allowed to plug 3 and negative a half in? No, because if you do, what happens to the denominator? 0. So at this point, all we know, it could be a whole or an asymptote. Well, do either of those terms cancel? No. If I look at this right here, and I ask you, what are the only terms that matter when x gets huge? Can you tell me one of them? X squared. The x squared matters, and what matters down here? 2x squared. Does any of this matter? Not at all. What's the degree on top? 2. What's the degree on the bottom? 2. The degree is both 2. We love it when the degrees are equal, because then what do you look at, Calvin? The leading coefficient. What's the leading coefficient here? What's it there?
2.
So what's the horizontal asymptote? 1/2. When the degrees are the same, all you need to look at is the leading coefficients. So in this case, can someone tell me what the horizontal asymptote is? No, that's the end behavior. Y equals 1/2. That's it. That's totally it.
X minus 3 times x plus 4.
Bingo. What's the bottom become?
X minus 3 and x plus 5.
Nice. So does something cancel?
X minus 3.
So that means you're going to have a hole. Where are you going to have a hole? What's the x value?
3.
And then you plug 3 into the... You plug in 3 to the other. And what do you get for the y value?
7/8.
Bingo. Nice. Now we're not done. What about the other one? 0 equals x plus 4 over x plus 5. So what's the y-intercept? Connor, what's the y-intercept?
The y-intercept is when you plug in 0 for y.
Yeah.
It's
Sorry, what's the x-intercept? I mean, what's the x-intercept? 0 for y, so what's it going to be? How do I make that equal to 0? What do I plug in for x to make that equal to 0? That would be the denominator. You want the numerator to be 0. You want 2x plus 4 to be 0. So 2x is equal to negative 4. So what does x equal? Oh, negative 2. How do you find the y-intercept? I circled it. How do you find the y-intercept? X equals 0. If I make x equals 0, what happens to what's in the circle right there? What's left? 4 over negative 5. So do we have 2 points right there? Yes, we have 2 points. We have 2 points. So now we have to be really careful about the next thing here. We know the vertical, where's the vertical asymptote? X equals 5. So there's going to be a dotted line at x equals 5 right here. And the function, when it comes from the left, is either going to go up or down. And when it comes from the right, it's either going to go up or down. We're going to figure out which one it is. We're going to figure out which one it is. So let's look at this right here. It's 2x, the limit as x goes 5 to the right of, what was it? 2x plus what?
2x plus 2 minus,
Over x minus 5, right? Yeah. So this means 5 from the what? Right. So if we're to the right of 5, are we greater than 5 or less than 5? We're greater than 5. If I put a number greater than 5 here, let's say 6, what's 6 minus 5? Is that positive or negative? Oh, it's positive, right? So if we're to the right of 5, this is always going to be what? Positive. And what's this always going to be? Positive or negative? If we're greater than 5, this is always going to be what? Positive. So we have positive over what? Positive. Positive over positive stays what? Positive. As you get infinitely close to 5, I have a question. As you get infinitely close to 5, what is infinitely close to 5 minus 5? It's going to be positive, but what? Really small. So like 0.11111. But as you get close to 5, what's 2 times 5? 10. What's 10 plus 4? So what does the top get infinitely close to? No, the top, just the numerator. 2 times 5 plus 4, what's that? 14. The top gets infinitely close to 14, but this gets infinitely small. What's 14 divided by a small number? A big number or a small number? A big number. Like what's 14 divided by 0.1? 140, right? What's 14 divided by 0.01? 1,400. As x gets closer to 5 from the right, this becomes really, really small positive, and this gets really close to 14. What's 14 divided by a small positive number? What does that get close to? A big, huge number. Is it positive or negative? Positive what? Infinity. So for this one right here, you're doing the same thing, but you're going from 5 from the what? Left of 2x plus 4 over x minus 5. This is going to be approximately, well, it's 14 on top. That stays the same. What changes about the bottom? You're coming from the left of 5, so less than 5. So like 4, what's 4 minus 5? Oh, so this is going to be a negative small number. What's 14 over negative small number? Really small. No, it's going to be what? Is it going to be negative or positive? Negative what? Negative infinity. So you put this all together. We need to take all of this information and see the, as Connor put it, the what? The drawing, so to speak. The drawing. So I'm going to take this right here and move it up here so we can put it a little bit closer. So y equals 2. So how about this one? Are the asymptotes part of the graph? No, they are just there for reference. Oh, okay. So you see those 3 dots? What could we do with those 3 dots now? What could we do?
Connect them except skip over the hole.
Except skip over the hole, exactly. So what could we end up with? Like this, and it goes to there, and then goes, oh, has to go down. Why do we know it goes down? We found out when you go from the left, it goes down. What does it go to when you approach from the right? Up. So this is going to go like this. So Connor, when you're thinking about it, we just answered your question about the sidedness. As x gets really, really big, it approaches from the top. As x gets really, really negative and big, it approaches from the bottom. We answered it visually, but you could think about it more. Keep thinking about it algebraically. Here's the thing. The more careful you are in your investigation, the easier this is.